Uh-huh. Так, смотрите, в прошлый раз мы поговорили про статические игры и про концепт равновесия по Нэшу для статических игр. Также, то есть мы поговорили про равновесие по Нэшу, а также мы для двух two-player zero-sum game. Кстати, мне, наверное, по-английски надо, да? Или там, если двое есть. Okay, so yeah, last time we checked two solution concepts for static games. So one was two-player zero-sum game, and for that we had saddle point solution concept. And more generally, we had general games, general static games, and for that we had Nash equilibria in mixed strategies. Okay, so for saddle points, the interpretation was that a profile of strategies sigma 1, sigma 2 for players 1 and 2 is a saddle point if in each of these strategy a player places a strategy which guarantees him some payoff regardless of what the opponent is doing. Okay, so it's a safe way to play. And it doesn't require primary coordination for rational players to play this one. Like if a player wants to be safe, he could just play. Like for example, if I play matching pennies game against you, I don't need to coordinate which strategies we're playing with you before that. I could just go ahead and play 50-50 heads and tails. And I'm gonna be safe. Maybe it's not the only thing I could play reasonably, but at least it's a safe solution concept. Okay, for Nash equilibria, things are much more tricky, in the sense that in general, and as we will see in this lecture, it requires much more. So if we ask ourselves a question right now, what's the reason for us to look at Nash equilibrium in a static game? Well, I could name you a few where this Nash equilibria could be expected. So one of them is self-enforcing agreement. The idea is the following. So suppose players need to play some game G. And in this game G, they don't know what to play at the beginning. But before they play the game, they meet and they coordinate on a strategy profile. Say sigma 1, sigma 2, maybe more than two players, but I guess let's assume two players for discussion. So player 1 and player 2, they meet and they say, okay, so hey, let me play strategy sigma 1 and let you play strategy sigma 2. Okay, they shake hands on that and then they go to their separate corners and start playing. So what happens next with strategy profile sigma 1, sigma 2? Each of them could say, okay, so hey, assume my opponent is playing sigma 2. So what do I do next as a reply, right? So if I think that my opponent is playing sigma 2, I myself may choose any other one a deviation. So if this thing, sigma 1, if it's the best reply against sigma 2, unilaterally I would have no reasons to deviate. And likewise, my opponent, she would have no reasons to deviate if she believes that I'm going to be playing sigma 1 if sigma 2 is the best reply against sigma 1. Okay, so if what they agree to is Nash equilibrium, then at least unilaterally they will not have a reason to deviate from sigma 1, sigma 2. Okay, and in such a case, maybe we could say that Nash equilibrium is going to be a stable agreement against unilateral deviations. In general, in a game, there are multiple Nash equilibria. So without prior coordination, it's not clear that rational players would play a Nash equilibrium. And even, as we will argue a little bit later today, even if there is a unique Nash equilibrium, still there's no compelling reason for rational players to start playing Nash equilibrium without prior coordination. Okay, but one way to play is just if they explicitly discuss and agree to play. Okay, second one is quite similar. It's a recommendation of a mechanism designer. Suppose players trying to play some game G, and they don't know what to do, or they could not agree themselves what to do. So they could invite into the argument, they could invite someone who they think is smart. Like maybe they hire some distinguished economist, and the economist looks at the situation at G and says, hey guys, why don't you play profile strategy sigma 1 and sigma 2? Okay, so he just does for them this problem of coordination and some agreement. And if it is commonly recognized that this guy is respected and everybody explicitly agrees to follow his recommendations, whenever he recommends a static Nash, I'm sorry, a Nash equilibrium, at least unilaterally, people would have no reasons to deviate. Okay, so it's almost the same kind of situation, except like in one they could reach an agreement themselves. Another one is just they require someone else to come into the room, and then they explicitly say that, well, we're going to follow his recommendations. So pretty similar. So the third one is a social norm. Okay, so that's an idea that maybe we are players in the game. We never had a chance to coordinate explicitly with us, or to invite a mechanism designer into the room so that he would help us to coordinate. But maybe in this game G is played in some society in which everybody, or almost everybody in the society is expected to know the rules of the game. Maybe they go to, so an example could be when you drive on highways in Russia, right? You are required to pass driving exam, driving test. Okay, so you need to learn the rules of how to play. Okay, so that could be a social norm. And if the social norm is a Nash equilibrium, when I, for example, see you at a road intersection, and I see a green line, green light for myself, I expect you to stop because you'll get a red light for yourself. Okay, so the slight difference between 2 and 3, so it looks almost the same, right? So like we have driver's school, or we have laws. Here we have mechanism designer who tells us what to do. The slight difference here, I would say, is that in one situation, we first pick 2 players, and then they see that everybody agrees with the rules. So they're certain that, for example, if it's N and Bob playing, they know that this particular N has just agreed to play sigma 1. This particular Bob has just agreed to play sigma 2. When I go and drive my car on a highway, and say I'm N, I don't know which one particular Bob it is. Most likely this Bob has passed the exam and he knows what the rules are. But maybe sometimes he's a different one. So there is slight difference between 2 and 3. But again, for static games, it is Nash equilibrium stable in 2 and in 3. When we'll talk about dynamic games, there's going to be a difference which will be manifested between 2 and 3. But for static games, we do not notice this difference, the subtle difference. So the fourth one, it's a learning. So sometimes maybe we have a large population of players, like people living in a society, and then they play this game G many times during their life. Maybe there is no explicit rules how this game should be played, like no recommendation, no social norm that player 1 should choose sigma 1, player 2 should choose sigma 2. But maybe players interact with each other frequently. And from the past history of play, everybody learns that it's better to play sigma 1 if you're player 1, and it's better to play sigma 2 if you're player 2. Okay, depending on the exact rules of the procedure, maybe this procedure converges to a static Nash. I'm sorry, I say static Nash just because static game here, to Nash equilibrium. It turns out that the precise limit point to which it converges may depend on the procedure, and sometimes it could converge beyond static Nash. Okay, so it could be larger, but at least sometimes it could converge to static Nash. Okay, so an example of 4, which is not a 3, could be the following thing. So, for example, when you drive a car in Germany, right, everybody passes driving test, so they know the rules how you're supposed to drive on highway. But then also they have this social norm which kind of appeared itself. It's never written in the textbook or in the code, that whenever you driving on the left line and there is a person behind you who is driving faster, this person could start switching on left turning light. Okay, and this is an indication that he needs to get a clear way. And this person understands it and just passes right. Okay, so they don't need to honk. They just do the left turning light. And then everybody understands. And it's kind of an example of a norm which was learned by people by themselves without any mechanism design or without any imposed rules on them. Okay, so there is a way to learn a Nash equilibrium if the game is played by people, maybe by the same N and same Bob against each other, maybe by different N and different Bob selected from a large society every time. Another example maybe is just, you know, how in Russia, for example, if I go everywhere on a sidewalk, I typically try to stay on the right part of the sidewalk. It's because we have, we started by driving on the right-hand side, and everywhere except maybe for Moscow subway, you're supposed to walk on the right-hand side. Okay, so the only thing in Moscow subway, you're supposed to walk on the left-hand side, and it's imposed by the designer as a social norm, because like when you enter a subway, they tell you that you need to stay on the right and pass on the left. Okay, but now it actually turns out that if you go to a country in which on the road they drive on the left-hand side, like Australia, for example. So when I was first time in Australia, I was a little bit puzzled. I walk on the sidewalk. I try to walk on the right-hand side of the sidewalk, and everybody is just like bumping at me. And it's kind of a norm which you know, it's never written anywhere that you should walk on the which side of the sidewalk you walk, but it kind of develops itself. And number 5 is evolution. So before that, we thought always 1, 2, 3, and 4. It requires that the reason Anne and Bob play Nash equilibrium is because they are rational, they're smart, they realize that if they deviate, they are going to be hurt. Okay, so the evolutionary justification for Nash equilibrium does not require a particular player to be smart. Basically, the idea is just player 1 and player 2, they are animals. They interact. Maybe it's animals from the same species, maybe like male and female from the same species. Or maybe it's a predator and the prey. Okay, and they each learn how to play, but not in a conscious way. Rather, you could think that there is a population of these animals, and each of them plays a strategy which is inherited from his parents. And the one which plays a better strategy has a higher chance of surviving. Okay, and after some generations go by, it may happen that what actually the play will converge to is going to be a Nash equilibrium. In the sense that people who are playing a best, animals who are playing a best reply against what the other party is doing, they will have likely a higher chance to survive, and they will have a larger number of descendants. And therefore, like, next generation is going to be more animals who play the same thing. The difference between 5 and 1, 2, 3, 4 is just this one is not about rational players. It's not about smart players. So here in this class, I'm going to be interested in smart players, because like the 4 for us, the main reasons we look for Nash equilibrium is 1, 2, 3, 4. Okay, and also we will not cover learning. And for us, therefore, the main discussion is going to be around 1, 2, 3. Okay. So now what it means that it means that if you have a game and you say to me that, look, I want to study a Nash equilibrium of this game, you need to specify me a reason why you look at Nash equilibrium precisely. Is it 1, is it 2, is it 3? Like, which one you want to describe? If you just saying that I want to study the behavior of 2 rational players in game G, and therefore I want to concentrate on Nash equilibrium, it's not going to be enough. Okay, so why is it not going to be enough? So here is the reason why. Okay, so suppose we want to study behavior of rational people in a game. So first of all, we need to define what's rational. What does it mean we have a rational player? Okay, so what a rational player does. So for example, suppose concentrate on 2-player games first, for simplicity. So suppose I'm player 1, and I see player 2, and I don't know what she's going to be doing. But then she has several strategies. Maybe she has strategy B1, B2, BK, right? I myself, I have strategies A1, A2, AL. So now I know if some profile of strategies AI, BJ is realized, what I will get G1 of AI, BJ. Right? I know what my payoff will be if I know for some reason that she will play strategy BJ. Pure strategy. But the problem is, like, when I come to the game, and I haven't had any prior experience with the player and didn't explicitly coordinate on something, I don't know what the player will be doing. Okay, so the first assumption for player 1 is that if he doesn't know what the opponent is doing, he assigns some probability measure to strategies of the opponent and says that this is my belief of what the opponent will be doing. Okay, so a rational player, it's a descriptive definition of rational player. Okay. First of all, he has some belief delta in S2 about what rational player 1 about what player 2 will do. Maybe some player 2 is so confident he says, well, I know she will play BJ, so that means that belief will be assigning probability 1 to BJ. Maybe player 1 is less confident. He says, I don't know what's going to be played. Maybe this strategy will be played with probability 10%, this one with probability 20%, with this one with probability 70%. The interpretation of this probability belief, so P, is not that player 2 actually is mixing. It's not that player 2 is playing a mixed strategy. It's just the interpretation is that player 1 thinks that there is state of the world, there is a state of nature in which player 1 plays B1. She chooses pure strategy. But maybe this state of nature happens with 10% chance. Then there is another state of nature, she plays B2, and so on. In this interpretation, we don't even require that player 2 is mixing. Okay? It's just this probability indicates that player 1 is uncertain which pure strategy player 2 will choose. Okay? So rational player should have a belief in this definition, and 2, player 1 chooses strategy A from his set of strategies that maximizes his expected payoff, G, I, A, B, according to his belief probability measure. Okay, so he says, look, I think there is a probability measure P of how my opponent is playing, and let me check which strategy to play. If I play strategy A1, well, this is going to be the payoffs I'm going to be getting. Let me compute the expected payoff. For strategy A2, let me compute the expected payoff, and so on. So if I'm a smart player, and I indeed have belief P, it's better be that I choose a strategy which maximizes my expected payoff. Okay, so this is the definition of a rational player. This is like, from now on, when I say a player is rational, this is what I mean. Okay, whenever he is uncertain about what the opponent is doing, he assigns some probability measure. So, okay, so it could, okay, so yes, good. Let's even extend it to mixed strategies. We allow player 1 to choose from mixed strategies as well. And so this definition also can be extended to n-player games. Like if I'm player 1, I have several opponents. I have probability belief on the set of their strategy profiles. Okay, and if I think, okay, so for n-player games, the situation gets complicated in the following way. So this belief can be either case A, P is delta of S1, I'm sorry, S2, S3, Sn, it's one possibility. And another one is P in delta S1 times delta Sn. Okay, so what's the difference between the two? One is the following. He says, first, the state of nature is realized, and my opponents come, and each of them chooses a pure strategy. And then I have a belief over the states of nature. There could be a correlation between them. So this is the strategy profile, and this thing, this mixture of these pure strategy profiles indicates that player one could have a correlated belief. He can believe his opponents play in a correlated way. Okay, this one is he believes about each opponent some probability belief, but he assumes that these probabilities are independent. Okay, so this is the set of these beliefs is a superset of this one for more than two-player games. Now, the next one is going to be a little informal. So for today, it's a definition of common knowledge. So now we have a definition of what it means that the player is rational. Okay, and say that in two-player games it's unambiguous. In three-player games and more, it depends whether we choose correlated beliefs or independent beliefs. So here is a definition. Common knowledge. A player in a game thinks that a statement call it A is common knowledge, CK, if one player thinks A is true always, always means that if he is uncertain, there may be several states of nature. He thinks that in all states of nature, A is true. And two, the player thinks that his opponents think A is common knowledge always. Always think always that A is common knowledge. Okay, so this is an inductive definition. So for example, suppose G is a prisoner's dilemma. G is prisoner's dilemma. So what does it mean? There is, I think there is common knowledge that we play prisoner's dilemma. Well, first of all, I think that in all states of nature, I have these two strategies, cooperate and defect. You have these two strategies, cooperate and defect. And if we choose a strategy profile, the payoffs will be according to the prisoner's dilemma. So I think this is a fact. And second, when I think about what you know, I think that, well, you yourself think that it's common knowledge that we play prisoner's dilemma. So what it implies that when I think what you think I think we play is that you know that we play, I know that we play prisoner's dilemma. And so on for any finitely many iterations of knowledge. I know that you know that I know that you know that we play prisoner's dilemma. For any finite number of iterations, this definition implies we have this knowledge. Why? Because the first one is the base of induction. The second one is induction step. We pass it to the head of the second player. Okay, and I say that some statement A is common knowledge if everybody in the game thinks that A is common knowledge. Okay, when just for simplicity I say it's common knowledge in a game. So, couple of things to comment here. So one is that it is inductive, it is well defined only for finitely many levels of common knowledge. Right, so I don't know what it means that, what is the implication of something being common knowledge on infinitely many rounds. Okay, but for at least, I'm sure for any finite number of iterations, I can understand what it means. And the second one is just, there may be common knowledge of something. Common knowledge, we play prisoner's dilemma. But in actuality, we don't have to play prisoner's dilemma. Maybe we're playing chess. Maybe we're just a little bit crazy. We don't see what we're doing. We may think that there is a common knowledge, or a player may think that it's a common knowledge. He plays some strategy or some game. But it doesn't have to be true objectively. Okay, so maybe one example is just from classic literature, from Brothers Karamazov. There is an episode in which Ivan Karamazov, he sits and talks to a devil. Okay, and maybe for him it's a common knowledge, he sits and talks to a devil. He knows he's talking to a devil. He knows that devil is talking to him and so on, and for him it's a common knowledge. And it's a well-defined thing, and you could actually even argue that he's a rational player in that instance. And in fact, he's maybe one of the most rational characters in the book. But it doesn't have to be true in an objective way, in the sense that maybe some other person enters the room and he would disagree that there's common knowledge. Okay, so when I say something is common knowledge, I do not imply that it has to be true objectively. It's just like everybody, or at least the player in the game, thinks that it's common knowledge, thinks that it's true. But this is what we need. We don't need any more. Because why we need this thing? We only need to understand what the player will do. It doesn't matter whether or not, say, a player thinks that he's talking to a devil. It doesn't matter for us whether he is in fact talking to a devil. What it matters for us is what the player does as a result. Okay, and we don't need to even discuss whether there is something which is objectively true, because okay, now, so suppose I want to understand, I have a game G, and suppose it's a static two-player game. Two-player, for simplicity, I will discuss a little bit later for n-player games. Static two-player game. Okay. So I want to understand what players can do in this game if they think that if there is common knowledge, they play G, And if there is common knowledge, they are rational. Okay, so the question then is, what the players can play under common knowledge of G and of rationality. Okay, so first, so is the question clear? Okay, so now first we need to understand what a player can play if he's rational in a game. So suppose we have a game, 2 players, A1, A2, AL, B1, BK. And suppose one strategy A, so I'm gonna be writing only payoffs of player 1, because I'm gonna be interested in just player 1 for a second. Okay, so suppose here are some payoffs for player 1 if he plays strategy A1. Okay, so here maybe 1, 0, 2, 3. Okay, and then there is another strategy A2, which in every cell, in every column, has a higher payoff than A1, strictly higher. For example, 2, 1, 7, 4. Okay, and now we have a rational player 1. He looks at this matrix. Oh, can it be that player 1 plays A1 ever? The reason, sure, because like if he has strategy A1 which is strictly dominated by A2, in this case we say strictly dominated, then he says, look, I don't want to do, if I ever want to play A1, if I switch to A2, no matter what my belief, I will do better. Okay? So definition, so a strategy sigma 1, a mixed strategy, strictly dominates strategy sigma hat in sigma 1 if for all B in S2 we have G one of sigma B strictly greater than G1 of sigma hat B. Okay, here sigma can be mixed, and in that case G is understood as a expected value of G. Okay, so we could extend the definition of strict dominance to mixed strategies. Oh yeah, yes. I'm sorry. So now, if I have two mixed strategies and one of them is strictly dominated, the strategy can be safely eliminated. A rational player can never play such a strategy. The question is whether the reverse is true. Suppose we have a strategy which is not strictly dominated. Is it true? Which is not strictly dominated by any mixed strategy. Because why for mixed strategy is important? For example, suppose we have the following matrix. So we have 4, 1, 1, 4, and then we have 2 and 2. Okay, so we have A1, A2, A3. So here in this matrix, if I just look at pure strategies, strategy 3 is not strictly dominated by any pure strategy. So it appears that maybe it can be played. But it is strictly dominated by a 50-50 mixture of A1, A2. Therefore, A3 cannot be played. So that means that we need to check strategies against domination by mixed strategies. Okay, so now it turns out that the reverse is also true. Okay, so we have a theorem. So that's the first theorem. Okay, so it's a consequence of rationality. So theorem 1 here is just a strategy sigma in mixed strategies of player 1 is a best reply against some belief P and delta S2 if and only if sigma is not strictly dominated. In among other mixed strategies. Okay, so one direction we have seen just now. Okay, so if it's a best reply, it's not strictly dominated. Okay, so let's prove the other implication. Suppose sigma is not a best reply. Is never a best reply. Yeah. It's just consequences of just being rational. It's not the consequence of being common knowledge of rationality. So now, a best reply means that if I have a belief P, in delta S2. Best reply against P is arg maximum for sigma in delta S1 of expectation G1 sigma B. It's a maximizer of expected payoff. So what this means is just for all P in mixed strategies of player 2, or in belief about player 2, we have A of P such that I'm sorry, sigma of P such that expected utility of sigma is smaller than expected utility sigma P. Right? So that's the definition. For every belief, we could find a better strategy. Let's choose any selection, sigma P. So now, let's introduce auxiliary game. Let's introduce the following game, call it Jihad. In this game, we have the same strategies, delta sigma 1, mixed strategies, and delta sigma 2. But for every sigma 1 and sigma 2, we have that payoff G of sigma 1 and sigma 2 is for player 1. That is this is a G of sigma 1 sigma 2 minus G of sigma. Let me yeah, okay, so let me sigma 0 here. It's G of P, G of sigma 0, sigma P, just to circle that strategy. Sigma 0, sigma 2. Okay, and then payoff of the second player, G2, sigma 1, sigma 2, is just minus G1, sigma 1, sigma 2. So it's a zero-sum game. Okay, so I basically took, for player 1, I took payoffs and I subtracted payoffs from the strategy of the strategy we're interested in. The one which is a never best reply. Okay, so I subtracted column by column. for all mixed strategies. And for player 2, I just said that he gets the negative of player 1 payoff. So it's a zero-sum game. Yes, G1. Yeah, I'm sorry. Yes. Yeah. Yeah, this is hot. This is hot. Okay, in the new game. So now this is a zero-sum game. It means it has a saddle point. Okay, so let sigma 1 star and sigma 2 star be the saddle point of it's a zero-sum game. We know it has a saddle point. No. So this is a payoff of player 1. Okay, it's non-zero. And payoff of player 2, just by definition, is a minus. Yeah, it's yeah. So now my claim is then claim sigma 1 star, the one from saddle point, strictly dominates sigma 0 in G. Saddle point of G. Saddle point. Nash equilibrium. Yes. I'm sorry. All of that is just for finite games. So okay, so let me prove it, right? What's the min-max value of player 1 in this zero-sum game? So we need to take minimum for pair in delta S2. Okay, so min-max value is just when the second player moves first, selects a mixed strategy, and then player 2 maximizes by selecting his own mixed strategy, sigma 1 in delta S1 maximizes G1 hot of sigma 1 pair. Okay, so no. It could be. All right. So first, so This min-max value for every p which I choose, this maximum is greater than 0 by assumption. Right? This is how we defined. This is by assumption that, yeah, here. For every pair which I choose, I have a strategy which does strictly better than sigma 0. Therefore, for every strategy P which I choose, I have a strategy for which this difference is positive. Okay, so for every fixed P, I have strictly positive thing. Now, this maximum function is continuous in P. Therefore, it attains minimum. So it's not infimum, it's minimum. Therefore, the minimum is strictly better than 0. For every point, it's bigger than 0. A fortiori, it's bigger for minimum. So it's bigger than 0. Okay, but now this min-max value is attained when we play the saddle point. It's just the property of saddle point. So when we play the saddle point, what we get? In particular, it is attained against every pure strategy of the opponent, or even against every strategy of the opponent. Okay, so when I play a saddle point, I get G1 for all P in delta S2. I get that what my value in the zero-sum game from playing the min-max, the saddle point against P is greater or equal than min-max value is greater than 0. Right? But now we can open this one up. This is, by definition, this is a difference between sigma min-max against P minus G1 sigma 0 against P. And we obtain that it's greater than 0. But this is a definition that sigma 0 is strictly dominated by sigma 1 star. Okay, so that's one possible way to prove this theorem. This is from article Pierce 1984, the one which introduced rationalizability. Because often in the literature, in textbooks, they prove this theorem by duality theorem from linear programming. But this is an alternative. So now, for two-player games, we understand what rationality means. It's just we simply delete all the mixed strategies which are strictly dominated. So let me just so suppose we start with players playing. Player 1 can play any strategy from sigma 1. Player 2 can play any strategy from this one. Now, what could happen if I delete all the mixed strategies which are strictly dominated for player one. What's gonna be the reminder? Is it always true that what remains, so say we delete, so let's define BR of player one of, so for any H2 in subset of just a moment. So suppose I start with a game. So at the beginning, the sets of strategies are convex. So now I do one round of elimination of strictly dominated strategies for player one. So what's left then is going to be a subset of this. Okay, so let's call it some subset H1. Is it true that this subset is convex? So I just take the full game and I strike out all of the mixed strategies of player one, which are strictly dominated. So what could be said about H1 which survives? What are its properties? So first of all, is it closed? So suppose we have a strategy which is strictly dominated. Okay, so some sigma strictly dominated. Then any strategy in the neighborhood of sigma is also strictly dominated. Right, because say sigma star strictly dominates sigma 0, then sigma star strictly dominates neighborhood of sigma 0. Therefore, when we delete something, we delete the open set. So what's left is closed. Okay, so now the second thing. So suppose we have a strategy sigma, strictly dominated, and then it. So suppose we have another strategy. Suppose we have strategy sigma, which survives in H1. So let A1 A M be pure strategies in support of sigma. So sigma survived. Is it true that every pure strategy in the support of sigma survived? Support means that sigma is mixed strategy, it's a pure strategies which are played with positive probabilities in sigma. So say I mix 50-50 between A1 and A2. That means that support is A1 and A2. It's like support of probability measure. So if sigma survived one round of elimination, is it true that every pure strategy in support of sigma survived? Okay, so we have sigma equals to some probability lambda 1 times A1 plus lambda L times AL. Strategy A is strategy AI is in support of sigma if lambda I is greater than 0. So sigma can mix all the strategies, then it has a full support. Sigma can play just one pure strategy, then the support of sigma is just one strategy. Or it could mix like 2 or 3 strategies, and the strategies which are mixed, which are played with positive probabilities. So the question is, suppose we delete one round of strictly dominated strategies, and this is a set which survived. Suppose we have a mixed strategy which survived. Is it true that every pure strategy A is in support of sigma? Is A in H1 as well? Right, because, well, if I'm willing to mix some strategies, that means that each strategy in support does at least as good as sigma itself. So if sigma is the best reply against some belief, every strategy in the support of sigma is the best reply. Okay, now, the next question, is it true that H1 is convex? So how would you, like, what's the definition of convex set? So so let's check. So suppose let's do the simple one. So suppose there are two pure strategies in H1. At least two pure strategies. Okay, so suppose we have A, which is in H1, and then we have A prime, which is also in H1, and they're pure. Okay, so now, is it true that every mixture of A and A prime is also in H1? How do you prove it? See, what the problem is? Like, if A is in H1, it's the best reply against some belief P. If A prime is in H prime, in H1, it's the best reply against some belief P prime. P and P prime may be different. They don't have to be the same. And now suppose we want to say that 1/2 A plus 1/2 A prime is an H1. We need to find some belief against which this one is. But it may be not P, not P prime. Neither of them may fit. So here is an example. I already had it, right? So just a second. Like that. So suppose we have three strategies A1, A2, A3, and they give us payoffs for 1, 1, 4, and then another one is 3, 3. So here, strategy A1 is a best reply against B1, and strategy A2 is a best reply against B2. But strategy 50-50 A1, A2 is not a best reply, because it's dominated by A3. Okay, so to sum up, when we do this deletion, we start maybe with a nice convex set, closed convex set. But when we do the deletion, what we obtain? We obtain a non-empty set, which is closed, which is not necessarily convex, but has a property that for every strategy, every pure strategy in the set, every pure strategy in the support is also in the set. Okay, so say that okay, so definition. So definition set H of delta S1 has pure strategy property if for all sigma in H we have support of sigma is in H. Okay, so every pure strategy in the support is in H. So we have seen that if we start from the full set and delete one round of strictly dominated strategies, we obtain non-empty closed set which has this property. Is a subset, yes. Oh, yes. Okay, so now let me define the following iterative procedure. Step 0, it takes some strategy H10 or some subset of mixed strategies of player 1 and some subset of mixed strategies of player 2. which are such that H1, H2 are non-empty, closed, and have pure strategy property. Okay, so whenever this three happens, let's call them nice sets. Okay, so let's start with two nice subsets of mixed strategies. Okay, and let me do the following procedure. In step 1, step 2, and inductive procedure. So suppose nice sets HT has been defined. H1T, H2T. So at step T plus 1, what we do? We do one round of the following thing. So for I, 1, 2, so for each player, how do we compute H I of T plus 1? It's by definition, it's the following. It's all such strategies in the previous set, such that for them there exists a belief in convex hull of the nice set of the opponent such that sigma is best reply against P. Okay, so basically the idea is just, look, so suppose I started saying, look, my smart rational players, I know they play some strategies from these nice sets, H1, 0, H2, 0. So what I conclude next? Okay, so next step I say, well, if player 1, he knows his opponent plays a nice strategy from here. So what does it imply? Well, it implies that, look, he must put some probability on strategies in the convex hull. Okay, so he could have some belief, and the sigma which he could play should be a best reply. Okay, and only such sigmas which survive this thing, they are left for the next step. So what's how I justify this thing? Look, if I have suppose I'm player 1, and I think that my opponent can play any mixed strategy from H2, 0. Okay, so H2, 0 is nice, it has pure strategy property. Let me define support of the whole set, H2, 0, as all pure strategies in H2, 0. Strategies ever played in mixed strategies in H2, 0. It's a finite set. So my claim is just when we have a convex hull of H2, 0 of a nice set, it coincides with convex hull of the support. Why? Because of the pure strategy property. Convex hull is just yes. Convex hull is a infimum of all convex sets which contain the set. So look, so my claim is if H has pure strategy property, convex hull of H is a simplex spent on the pure strategies which are played in each cell. So by pure strategy property, everything is there. Like it should be self-evident, really. Yes. So in the definition, what it actually says, look, we have a player who, after some thinking about the opponent, concluded that the opponent can choose strategies from H minus 1t. Okay, so this is player 1 thinks that the opponent, player 2, must play some strategies only from here. Now, player 1 is uncertain which one. Maybe player 2 thinks that there is some mixture over these mixed strategies. In some state of the world, player 2 plays one mixed strategy. In another state of the world, he plays another. All in all, it's going to be some convex combination of these strategies. And the belief of player 1 has to be a convex combination, a probability measure on convex combinations. But now, all these convex combinations, they really can be represented by a convex combination of pure strategies in the support of H. So really, any probabilistic belief of player 1 about what player 2 is playing is equivalent to probabilistic belief in that simplex. So the next proposition. So for now, let's not overthink the interpretation. It's just basically, look, you have a nice set. This thing is a simplex. This thing is a simplex. It's an element of simplex, and we have a definition what best reply is against this probabilistic belief. Right. So now the following proposition. Let H10, H20 be nice. All right. So this is just nice subsets of mixed strategies, meaning closed, non-empty, and satisfy pure strategy property. Then, for all t, for all steps, we have H1t. It's a subset of delta S1, and the H2t is a subset of delta S2 are nice. First thing, and the second thing is just the procedure. Look, every next step diminishes the set because we throw away some strategies. The procedure stops infinitely many steps. There exists n such that for all t greater than n, h I t equals to h I n. There is some finite n at which it stops. So suppose HT is nice by induction, right? So then HT plus 1 is non-empty. Because, look, take any probability here, there's a best reply. Because best reply against P in H I of T. Meaning that definition is sigma is argmax for all sigma hat in H I T of expected utility. We take the best reply inside of the set. Also, we can prove that if all the previous sets are nice, the new set is closed. The proof can be done by the standard arguments. Take a sequence of sigmas in this one. Take a conversion subsequence of strategies and beliefs which converge, and by continuity check then the limit is also in h t plus 1. Okay, so it's just a standard argument how we prove that the set is closed. And also it has a pure strategy property. Why? Because, well, suppose we have some mixed strategy, it's in HT. Okay, and it's the best reply. It's the best strategy in HIT against some belief. Then every pure strategy, by definition, by HT being nice, is also feasible to choose from. Because the previous set had pure strategy property. And therefore, every pure strategy must give exactly the same payoff against P as the mixed strategy. And therefore, the new set has the pure strategy property. Now, why this procedure stops infinitely many steps? So let's keep track of convex hulls of HIT. So as I said, what's convex hull of HIT? It's just it's a simplex, which is spent on pure strategy in the support of HIT. At every step, what could happen? Some of the simplexes could become smaller, could lose a dimension. or it could stay the same. Now, we started from a finite game. Simplices cannot keep losing dimensions. Okay, so after some step, there exists some n such that at n and at n plus 1, no simplex has lost a dimension. And then my claim is then from this point on, hi n plus 1 is the same as hi n plus 2. So basically, I had some hin, and it contains strategies which were best reply against some simplex delta, so with some dimension k. Okay, each strategy, each in hn plus 1 was the best reply against some simplex beliefs in p delta k. And it was a subselection from hyn. But now, I hold this subselection from hy and n plus 1. I need to find best replies within this set against the same set of beliefs in the previous step. Every strategy was here was a best reply even in the larger set against the same set of beliefs. Therefore, it's a best reply in a smaller set as well. Therefore, at step n plus 1, the strategy stabilizes, the procedure stabilizes. Oh, it should, we should have stopped at some point, not? Я просто... Да. Ну, давайте тогда на 10 минут сейчас прервемся. Так, давайте продолжим. То есть у нас, смотрите, что получается. Мы, когда берем какие-то два nice subsets of mixed strategies, we and start this iterative procedure. We obtain a decreasing sequence of a sequence of decreasing sets, which stabilize at some finite point. Okay, let us define, denote R1 of H10, H20, and R2 of H10, H20. Limits of the procedure. So we start with some nice sets, and this is where we converge for player 1, this is where we converge for player 2. Okay, so now another one definition. Subsets R1 of this delta S1, delta S2, subset of delta S1, and likewise R2 S1, delta S2, are called subsets of a rationalizable strategy. Okay, and this solution concept, which for the game gives these subsets, is called rationalizability. Okay, so we have a game, G, and what it says, rational players under common knowledge of rationality, they can play any mixed strategy from here and from there. This is a procedure which we start from all mixed strategies. Okay, let me justify this relation to common knowledge. Okay, for that we need just one more definition. Definition Best response property. A1 okay, we have two players, let's say A and B. Subset A of mixed strategy of player 1 and B non-empty. B of strategy of player 2 have best response property if for all x, for all sigma in A, we have that there exists P in convex in delta of convex hull of A. No, just in convex hull. In convex hull of B, such that sigma is a best response for player I against P. Okay, and this best response is among all strategies, not necessarily in set A. And the same for player 2. For all sigma in where there exists P in convex hull of A, such that sigma is a best response for player 2 against P. In words, suppose we have players, and it is said that it's commonly known that every player plays some mixed strategy. Player 1 plays mixed strategy from A, player 2 plays some strategy from B. My claim is that if A and B have best response property, this pair A and B has best response property, then it doesn't contradict common knowledge of rationality. Indeed. So suppose, so it's basically like players indeed can play every strategy from A and B under common knowledge of rationality. Indeed. Player A, so take any strategy sigma from A. Player 1 can play this strategy because he says, well, I know the only thing that my opponent plays strategies from B. I can find some mixture, I can find some belief in this B, some mixture that my strategy will be best reply. But then for every strategy of my opponent there, I can justify my opponent plays strategy because he can find a belief in my strategies, which are best response, and so on. So basically, for every strategy here, I can find a belief on admissible strategies of player B, such that yes. So it's basically, look, so conjecture of player 1 is player 2 can play in every state of the world, can play some strategy from B. That means that the belief of player 1 could be any linear combination of the strategies from B. Okay, and against, we can find such a belief that strategy sigma indeed is optimal. It's the best reply among all the strategies, and it's rational for the player to play it. Then player 2 for every strategy B in B, he knows that player 1 can play any strategy from A. Therefore, his belief should be in the convex hull of A. But he can find such a belief which justifies B. It could be rational to play B, every strategy. So player A coming back, in his belief, he can justify the choice of every strategy of B by rationality. In turn, he can also justify that player B can justify every choice of player A in her beliefs, and so on. And so on for any finitely many levels of reasoning. Okay, so let me give you an example of a set which satisfies best response property. Example. Any Nash equilibrium sigma 1, sigma 2 satisfies best response property. Right? It's by definition of Nash equilibrium. A strategy is in the Nash equilibrium, it's a best reply against unconditional best reply against the strategy of the opponent. So a pair of singleton sets, sigma 1 and sigma 2, it satisfies best response property. So now we come to the answer to the question. So suppose we have players and we think that it's common knowledge that they play game G, and it's common knowledge that they are rational. What could be a possible solution? Well, maybe a possible solution can be any pair of sets A and B which satisfies the best response property. And the union of such pairs, because like example, we don't know which particular set they will choose. Maybe they will choose a Nash equilibrium, maybe they will choose something bigger. So let's introduce the largest possible sets of strategies they can potentially play as the following. Definition for all I 1, 2, define EI as a set of all strategies sigma in delta S1 such that there exists a pair of xi x minus I such so satisfying best response property such that such that sigma is in xi. Okay, so let's take the union of all the strategies which are ever played in sets which have this best response property, which are ever played in combination in which players can justify the strategies of each other. Okay, and then the proposition which ends the construction is just for all I, we have EI equals the set of rationalizable strategies. Meaning that what we have found is that procedure is indeed the answer for this interpretation of common knowledge of rationality. Okay, so let me prove this proposition. So first, Ri is contained in EI. So I'll drop this thing here. Why? It's just by definition of EI. Rationalizable sets, they just best reply to each other, to this convex hulls. So rationalizable sets, they satisfy this best response property. Therefore, they are contained in EI. Next, we need to check that EI is in Ri. But, you see, the thing is, let's recall this procedure, this iterative procedure, which computes as rationalizable sets. EI, for sure, is a subset of H0 of that procedure, which was the whole set of polarized strategies. Now, every strategy in EI must be a best reply against some strategy, therefore must survive the first round. Therefore, EI will be contained in HI1. And so on by induction. For all, we can prove by induction that for all t, EI is contained in HIT. But therefore, EI is contained in the limit of this HI, which is Ri. Therefore, they must be equal. Okay, so now it means that every pair of sets which satisfy best response property is a subset of rationalizable sets. And rationalizable sets are the largest sets which satisfy this best response property. So now, what's the first corollary of that? So corollary 1 is that every Nash equilibrium is rationalizable. Is a pair of rationalizable strategies. Nash equilibria Nash equilibrium strategies are rationalizable. The second thing is just how do we find the sets of rationalizable strategies? One procedure to do this is the following. So we have a game G. Originally, it could be very large. So what we do is just we find any strategy of any player which is strictly dominated. Okay, and then we cross it out. So for example, suppose we have found that some strategy AI is strictly dominated. Pure strategy is strictly dominated by some mixture. We cross it out. We obtain a smaller game. In a smaller game, it's going to be easier for us to find strictly dominated strategies. We may find another one, and so on. And we continue crossing out strategy after strategy after strategy, until we no longer could. Okay, so the procedure starts with some subsets of pure strategies. Here, say A, and here, say B. My claim is these are precisely pure strategies which are rationalizable, no matter what was the order of deletion of strictly dominated strategies. How to justify this answer? Well, first of all, when we delete a strategy which is strictly dominated, by theorem 1, the dominance theorem, we delete precisely the strategy which is not a best response, which is not possible. Right? So if we delete after some procedure a strategy, that means that it cannot be just a second. By induction, so suppose we have this deletion of strictly dominated strategies, and it proceeds in some n rounds. My claim is every rationalizable pure strategy has survived. To prove it, one can do induction. At step 0, we have all the rationalizable strategies are not deleted yet. Rationalizable pure strategies are not deleted yet. Now, at step 1, we delete some strategy which is not a best response. Therefore, look, every rationalizable strategy is a best response against the rationalizable strategies of the opponent. Therefore, at the first step, we cannot delete the rationalizable strategies. Now, in a smaller game, still, any rationalizable strategy is the best response against rationalizable strategies of the opponent, which is still present by induction hypothesis. Therefore, in the next step, we could not delete rationalizable strategy, and so on. So in every procedure, we could not delete a rationalizable strategy. Suppose we continue this procedure. So that means that if we take elimination of strictly dominated strategies and stop somewhere, we did not throw away rationalizable strategies, right? That's the first claim. The second claim is just that we, for sure, will throw away all other pure strategies. Why is it so? Suppose we have this rationalizable strategies for player 1, rationalizable strategies for player 2, and we have not thrown away some other strategy. Okay, so we have some strategy set A, which contains rationalizable for player 1, and strategy set B, which contains rationalizable for player 2. And maybe at least one of them is bigger than rationalizable. Because we could not throw away strictly dominated strategy anymore, sets A and B, they have this best response property. We could not throw away means that in the game, which contains A strategies and B strategies, no strategy in A is strictly dominated, means that it's a best response against some strategy in B, or a mixture. And every strategy in B is a best response against some mixture of A. That means that A and B has best response property. But by the previous proposition, that means that the containment should be in the other direction. That means that A should be equal to this one, B should be equal to this one. So now, what it suggests is the following. Look, every Nash equilibrium, maybe in mixed strategies, should use rationalizable strategies. In particular, in the support of every Nash equilibrium, strategies which can be pure strategies which can be played are only those which are pure strategy rationalizable. But to find these pure strategies which are rationalizable, we can proceed in just elimination of strictly dominated strategies, one after another. And we obtain this rationalizable strategy no matter what the order. Right? So this suggests the following simple procedure for finding, a simplification procedure for finding Nash equilibria. Suppose I give you a large game, like say 4 by 4, and I ask you to compute its Nash equilibria. So what you could do is you could start first eliminating strictly dominated strategies. And then you obtain a smaller game. And for this smaller game, maybe it's easier to find Nash equilibria. This procedure guarantees that you do not throw away any Nash equilibrium even in mixed strategies. Okay. So we will get an example. But before we go, let me just discuss one more thing. So here the procedure was the elimination of strictly dominated strategies. The definition of rationality was that that a player forms some assessment P on the set of opponent strategies and best replies. For two-player games, it's equivalent. The player doesn't play strictly dominated strategies. Also, this whole procedure can be extended to n-player games with the definition of rationality that the player thinks that can form belief about the opponents which is correlated. Like, player can think that the opponents can play correlated strategies in a correlated way. This whole procedure applies. Theorem 1, the dominance theorem, still holds. It's essentially it's a two-player game in such a case. If we allow mixed strategies, then rationalizability is not equivalent to deletion of strictly dominated strategies. So now, the question may be, look, sometimes rationalizability helps to simplify the game. We throw away non-rationalizable strategies, even if our task to find Nash equilibria. But it is not very strong in many games. For example, the following game. So we have game G, which is 1, 1, 0, 0, 0, 0, 0, 0. So here, every strategy is rationalizable. Even strategy which is not very good. Why? Because this strategy, A2, is the best response against strategy B1. Like, if player 1 thinks that with probability 1, the opponent plays B2, then it's the best response to play A2. Even though by playing A2, player 1 always gets 0. By playing A1, he gets 0, but maybe sometimes 1. So maybe one may wish to extend definition of rationality to the following thing. Player 1 is rational if he forms belief P inside of delta 0 of S1, meaning full support belief, and then best replies. So basically the idea is, look, in the original definition of rationality, we thought that player can, for any assessment, maybe put in zero probability on some strategies. Let's define now a different one. Let's say it's a cautious rationality. Cautious meaning that player is not sure. Maybe he will most likely play B2, but maybe there is a small probability he will play B1. In such a case, if a player 1 is rational, he can play A2. But if a player 1 is cautiously rational, he cannot play A2. Because against any full support assessment, this one is better. It gives positive payoff. Right? So now, for two-player games, we can obtain the following theorem. Strategy sigma in delta sigma 1 is not a best response against any P in delta 0 fs2 if and only if sigma is weakly dominated. I'll just explain. So what's weakly dominated? A strictly dominated strategy is strictly dominated by some mixture, meaning that against all strategies of the opponent, the dominating strategy is bigger, strictly bigger. Weakly dominated means that the dominated strategy is weakly bigger against all the strategies of the opponent. And for some strategy, it is strictly bigger. So for example, here, strategy A1 weakly dominates A2. Okay, so here, 1 is greater than 0, 0 is greater or equal than 0. So for some cells, there is equality. For some cells, it's strict inequality. For strict dominance, we had to assume that each entry is strictly bigger than the corresponding entry. For weakly dominated, we allow some of them to be equal. Okay, so it actually turns out that for two-player games, we can prove that a strategy is not a best response against against any assessment with full support if and only if it is weakly dominated by some mixed strategy. Okay, so and then it maybe suggests, look, it seems like cautiously rational players, like rational player, is a player who doesn't play strategy which is strictly dominated. A cautiously rational player here is a player who doesn't play a strategy which is weakly dominated. So maybe we can take rationalizability and start doing elimination of weakly dominated strategies. Okay, so, and typically finding weakly dominated strategies, like there could be strategies which are weakly dominated but not strictly dominated. And elimination of weakly dominated strategies typically is much stronger than elimination of strictly dominated strategies. But first thing, elimination of weakly dominated strategies may kill some Nash equilibria. Okay, so it kills this one here. When we do elimination of weakly dominated strategies in this game, we obtain this one. Another problem with elimination of weakly dominated strategies is that now, if I start the procedure of just eliminating weakly dominated strategies one by one, the answer may depend on the order in which I do. So let me give you an example here of a particular game. So the game has 3 strategies. A1, A2, A3, B1, B2, B3. One, two, 2, 3, 0, 3, 2, 2, 2, 2, 1, 3, 2, 2, 1, 0, 0, 1, 0. Now, so let's think about, so this is a game, we'll try to eliminate some pure strategies which are weakly dominated. So one way to strike out with first way, one way. We strike out strategy A1 because it's dominated by strategy A2 weakly. 1 is smaller than 2, 2 is equal to 2, and 0 is smaller than 3. We can strike out A1. After that, we obtain the smaller game. So in this smaller game, we can eliminate this one to 0 because it's worse than to 1. For example, one possible way. Okay, so we eliminate B3. After that, we obtain this game. In that game, we can eliminate the bottom one, 1, 0, because it's smaller than 2, 1. Strictly. Okay, so we eliminate A3. And finally, we eliminate B2, because 2 is smaller than 1. So after this game is reduced to this thing, we can eliminate B2 because 1 is smaller than 2 in the small game. So we eliminate B2, and what's left is this cell, which is A2, B1. Okay, so here I have simplified the game by deleting weakly dominated strategies. Now, I could have done it a different way. The bottom strategy, 2, 0, 1, it is smaller than the middle strategy, 2, 2, 3, right? 2 is equal to 2, 2 is greater than 0, and 3 is greater than 1. So let me eliminate A3 first. So second way. I first eliminate A3. Now I have this smaller game. Then that smaller game, like this 2x3 game, I can eliminate this strategy 2, 2, because it's smaller than 3, 2. So I could eliminate B1. After that, I have this smaller game. And here, 3, 1 is smaller than 3, 2. It means I can eliminate B2. And finally, in this game, I can eliminate A1 because it's 0 is smaller than 3 in the remainder. So I obtain so I eliminate A1 and I obtain this thing. 3, 2. And similarly, you could check there is one more way in which I do A1 first. Well, we could do it because similar. Then I do B2. After I eliminate A1, I could do B2 because it's 1, 0 smaller than 2, 1. Then I eliminate as well 2, 0 is smaller than 2, 1. I obtain this thing. No, but it's the same. Okay, but nevertheless, okay, so first and second way, they show that already the procedure could converge to different things. For strictly dominated strategies, we wouldn't have it. Other strictly dominated strategies in this game, 2, 3, 3. I think there are. Okay, so what would be the rationalizability procedure? So for sure, how we compute rationalizability or rationalizable pure strategies? We need to take the first round and eliminate all of the pure strategies which are strictly dominated. So let's find them. So A1 gives 1, 2, 0. 2, 2, 1. Are there any strategies which are okay, so in this game, every strategy is rationalizable. Because every strategy can be a best response against some other pure strategy. In particular, this set of strategies satisfies best response property. A1 can be a best response against B2. A2 can be a best response against B3. A3 can be a best response against B1. Even against pure strategies. Likewise, B1 can be a best response against A1 or any mixture of A1 and A2. B2 can be a best response against A1. B3 can be a best response against A1. So rationalizability has no bite here. Deletion of weakly dominated strategies has some bite, but then it depends on the order. The question is what to do about this game. One answer is, look, there is a particular order of deletion of weakly dominated strategies which can be justified. This order is called iterative admissibility. And what is this procedure? This procedure takes the following. It takes the game and in the first round deletes all the strategies, all of the pure strategies, which are weakly dominated by some mixture at once. Not one by one, but at once, for player 1 and for player 2. Then in the smaller game, the second round, it deletes strategies, and so on. So in this particular order. So what would be iterative admissibility for this game? So how do I do? I take strategy A1, it gives me 1, 2, 0. It's weakly dominated by 2, 2, 3. Okay, so I delete this one for sure. in iterative admissibility. This one also, 2, 0, 1, it's weakly dominated by 2, 2, 3. So I delete this one for sure in step 1. So in step, so the only one which survives for player 1 is this one immediately. For player 2, I take the full game. I have 2, 2, 1, 3, 1, 0, 3, 2, 0. So 3, 1, 0 is dominated by 3, 2, 0. Okay, so I delete this one for sure. And then the question is, can B1, B1 doesn't weakly dominate B3, B3 doesn't weakly dominate B1. Therefore, they are undominated by mixtures. There's no point in mixing with the dominated one, so we just check one doesn't weakly dominate another. Okay, so that means that in the first round, what survives is just this one, this cell, plus this one. So only these two strategies survive. Now for player and these two cells. Okay, so these two strategies, B1, B2, and A2 for player. So A2 and B1, B3 is the outcome of iterative admissibility. After one stage, it stops. Okay, and this procedure of weakly dominant strategies, it has some justification in the language of common knowledge, like in the style. We will study it a bit later. Also, the thing is, right, we had an example in which elimination, iterative admissibility here for this game, in one round, it deletes these two strategies. It throws away some Nash equilibria. Say that Nash equilibrium sigma 1, sigma 2 is strict. Nash equilibrium sigma 1, sigma 2 is strict. If for all sigma not equal to sigma I, we have that sigma is strictly worse against so what's the Nash equilibrium? Nash equilibrium is an equilibrium in which every deviation is weakly worse for player 1 and for player 2. In strict Nash equilibrium, every deviation is strictly worse. Okay, so now the claim is if we have a strict Nash equilibrium, it survives elimination of weakly dominated strategies no matter the order. Okay, you could prove it at home. The proof is by induction because, well, suppose every strategy, a strategy profile sigma 1, sigma 2 has survived so far, and it's a strict Nash. Then sigma 1 could be a best reply against the following mixed full support assessment. It puts almost all of the weight on sigma 2 plus some of the weight on the remainder. And this would be like a full support assessment for which sigma 1 is a strict best reply. But okay, so let me just give you a couple of examples. So some Suppose we have the following game. It's 3 by 4. A1, A2, A3, B1, B2, B3, B4. No, it's by 3. Now we have 7, 3, 6, 3, 5, 5. 7, 3, 6, 3, 5, 5. 4, 7, 5, 8, 6, 9. 4, 7, 5, 8, 6, 9. And then we have 4, 2, 5, 8, 8, 6. 4, 2, 5, 8, 8, 6. And then I have 6, 1, 3, 8, 2, 4. 6, 1, 3, 8, 2, 4. Okay, so such a pair of matrix. Okay, and now suppose I ask you to find all of the Nash equilibria in pure and mixed strategies. Okay, so how would you find pure strategy equilibria? Well, you just circle the best replies. Okay, so let's do it. If player 1 plays A1, the best reply for player 2 is this one. Right? Oh, yeah, 7. Yeah, I'm sorry. This one. If player 1 plays A2, the best reply is this and this. Right? If player 3 plays this one, the best reply is 1, 8, this one. 9, sure. Right. Now, if player B, so I'm gonna circle for player B with a different color. If he plays B1, the best reply is this one, right? If he plays B2, the best reply is this one. If he plays B3, the best reply is this one. And if he plays B4, the best reply is this one. So this one is a Nash equilibrium in pure strategies. A3, B4. Okay, so A3, B4 is a pure strategy Nash equilibrium, P and E. Now, what about mixed equilibria? One naive way would be just to start checking all of the possibilities of which strategies are mixed by player 1, which strategies are mixed by player 2. But it would be a lot. Instead, what we could do, we could try to eliminate dominated strategies, strictly dominated strategies. Okay, so let's see if there are any strictly dominated strategies. B3 is dominated by B4. 5, 6, 4, 7, 8, 9. Good. Right, so we can delete this one. Okay. So now we have a smaller game. 7, 6, 4, 4, 5, 5, 6, 3, 6. Okay, so far we can delete B1. Okay, 3, 2, 1, 3, 8, 8. Yes, we can delete. No, it's weakly. Yeah. But with before. 3, 7, 2, 8. Yes. Okay, so we can delete this one. Now we have a small game. So now we have 6, 4, 5, 5, 3, 6. It doesn't seem that it's dominates anyone for the first player. No. B2. Yeah. Okay, so B2 is weakly dominated. The only way B2 can be played against, but not before, is if player 2 plays A2 with probability 1. Yeah. But what I'm saying, suppose player 1 plays A2 with some mixture. Then B2 is strictly worse. Okay, so now the question is, can player 2 play A2 with probability 1 in Nash equilibrium? So if he plays A2, then the second player mixes between B2 B4. Okay, so because he's indifferent. What could be a mixture? Okay, so the conjecture, right? So Nash equilibrium A2 and some mixture P. Okay, so alpha B2 plus 1 minus alpha B4. Okay, so what could be the mixture? The mixture should be such that player 2 indeed wants to play A2. So if he plays A2, he gets 5, no matter what. So it should be that in other strategies, he gets less than 5. So it should be that 6 alpha plus 4, 1 minus alpha is smaller than 5. And 3 alpha plus 6 times 1 minus alpha smaller than 5. Okay, so this one gives me 2 alpha smaller than 1. So alpha has to be less than 1/2. And this one gives me minus 3 alpha 1 and then 3 alpha. So alpha has to be greater than 1/3. So Nash equilibrium is this one with alpha in 1/3, 1/2. It's a Nash equilibrium. So now, in every other, what's that? Inside. So alpha has to be greater than 1/3 and smaller than 1/2. The Nash equilibrium then is A2 and alpha B2, 1 minus alpha B4. Yes. 6 alpha plus 4 minus 4 alpha minus 5 gives me alpha smaller than 1/2 or equal. Any other Nash equilibria? Yeah, the Nash one, like this is we already have. Okay, this one. Now, the claim is there are no other. Why? Because in any other equilibrium, player 1 plays some other strategies besides A2, which makes before a strict best response. So player 2 wouldn't mix. But if player 2 wouldn't mix, A wouldn't mix either, so he would play this pure strategy. Okay, so therefore for this game, we obtain that there are two sorts of equilibria. One is unique pure strategy Nash, and then there is a continuum of mixed strategy equilibria. All right. Maybe this is what. So right now we are running out of time for lecture. I think what I will do, I'll just send, I'll type up the lecture notes in the next week or so. And I will also send you a list of some practice problems. It's not gonna be like this problems for the course, but just for you to practice, like how to find Nash equilibrium and so on. So to reinforce the material. Okay. You are all from different groups, right? That I'm not sure. Like my LMS, у меня LMS не очень хорошо работает. А что такое? Телеграм-канал курса или телеграм? А телеграм-канал это телеграм-канал курса или да, слушайте, а можете меня туда как-то пригласить или что, я туда могу что-то там выкладывать? Ага. Вот, я тогда что-нибудь тогда пришлю какие-то эти смыслы.